For the final talk this afternoon, we have Hélène Esnault speaking on the crystallinity of rigid flat connections revisited.
So thank you very much for the kind invitation. It's always a pleasure to be here, to see, to feel also welcome. So thank you very much. And I have to say a few things before starting the lecture. So it's a second time I give a serious lecture on the method here, the background of the method. The first time was at the beginning of the fall at IHES. Dr. Garber was in the audience. So it is as it is. So I had much less time to say anything. And, in fact, one of those questions was kindly answered by Sasha. So this was wonderful. And here, offer is not here, so I have to fill in the time. And on the other hand, I just arrived from Hong Kong. I arrived at 5 a.m. at JFK this morning. So I hope you have a tiny little bit of compassion. So this is one thing. The second thing is I will read. So this was one thing I wanted to say before starting. And the second thing is that we uploaded the preprint with Michael like 3 or 4 weeks ago. And I was extremely pleased and also very impressed to receive a very warm email by Peter Schulze, like 2 hours before it showed up on the archive, telling me he was so pleased because he understood now what is really behind, but lemma such and such is wrong. Indeed, lemma such and such was wrong. That doesn't affect anything on what I'm going to explain. The revision is prepared. I'm going to upload it in a few days. And I'm not going to talk at all on this one part where lemma such and such is wrong. And this lemma such and such is wrong, it affects something I'm not going to talk about, the vast generalization on stacks of what I'm going to explain here. So, but nonetheless, I will mention the generalization because the lemma finally is correct with the proper formulation. And in fact, it is related to the beautiful talk by Martin this morning. How to define a Frobenius only one modulo. Okay, so those are general remarks and remarks before the talk, and now remarks really concerning the talk. It's really revisited because the history is like this. I said just in words, if we do complex geometry and we have a smooth projective variety on this complex variety, and we can look at complex linear local system, so not like Ananth with general groups, but complex linear. This has a moduli space, with the points of which parameterizes some simple local system. I don't take the stack, I take really the GIT moduli space. And then this GIT moduli space has isolated points. Those are called rigid local systems. And then Simpson devoted a large part of his milestone article on rigid local system, postulating in particular that they should come from geometry. So if they did, they would have plenty of properties which one can try to check first. And one property I'm not going to talk about, in fact, a friend of mine was joking with me because it uses p-adic methods, and he was telling me if you come to a p-adic conference to the institute and you talk on p-adic methods, they will kill you. So it was really purely it used the Langlands correspondence and the conjecture of Deligne. And the second thing we prove is that in the projective case, when we restrict our connection to a p-adic model of the variety, which is unramified, so which is defined over the Witt vectors of a finite field, then if it was coming from geometry, as we heard by Kiran Kedlaya this morning, it would be endowed by a Frobenius structure. And this is what we proved, but we proved this for infinitely many close points of a scheme of definition over Z with residual characteristic large enough. So the new method here, which is partly based, I can say immediately before I forget with jet lag, which is partly based notably on the work of Kestutis on the strong topology, not on the scheme, but if you go to the stacks on which I'm not going to say anything. So this bypasses this restriction, and we obtain just, it will be a purely local theorem, which will enable us to say at the very end, if we come from complex geometry, it's going to be fulfilled by all points of open of definition. So this is one thing. And the second thing is that, as you may have heard of, Jacob Zimmerman and Jonathan Pilar and Anand Shankar, in order to finish the proof of the André-Hort conjecture, they had to prove that if you have a Shimura variety, excuse me, of real rank at least 2, that means an exceptional Shimura variety, then it is, so then we know that all local systems are rigid. And so then we are in the situation we had analyzed earlier on with Michael, but not necessarily, we had analyzed only on a proper variety, in fact, projective variety. And those Shimura varieties, there are many of those which are not projective. So they needed a generalization of our theorem. So they asked us to prove the generalization. So we could prove this crystallinity property now for almost all P, said roughly, but those Shimura varieties have a very, very strong homological condition, which says that first the category is semi-simple, and secondly, it is the case that not only the complex local systems are rigid, but they are strongly homologically rigid. That means that if you look at the Zariski tangent space of the moduli on the open without any boundary conditions, then the Zariski tangent space is 0. So that says two things. That says that the point is smooth on the moduli, it's isolated and is smooth, and in addition, this moduli where you don't fix boundary conditions at infinity is way larger than the one where you fix conditions at infinity. So it is smooth even in this large modular space. So this is clearly a very strong assumption. And the proof I'm going to present is we bypasses this completely. There is no homological condition. So I hope it recasts a little bit in history what happens. And so it was interesting applications, obviously. And so let me write the assumptions, write the theorems, and comment on the terminology we are using, and then tell you what is the main tool and the main point in the proof, and then stop here. Okay? You can ask more, for example. So the assumptions are like this. So we give, so as I said, I forget completely complex geometry. So there's no complex geometry. So we just have, otherwise I'm going to be killed again. So we have just here a quasi-projective, a smooth quasi-projective variety over W, and W, that's really the V vector of a finite field, together with a good compactification. So good compactification means that the boundary closed subscheme is a relative normal crossing divisor with smooth components, all defined over W. So that's one piece of assumption. And then, as you saw, maybe I'll write the divisor at infinity. And then we write the components. And we use the terminology FQ for it's already here, and capital K for the field of fraction. And then we assume that the residual characteristic, so P, is at least 3. And in fact, it showed up this morning in the lecture by Karen Kedlaya, because of the fact that we can define a Frobenius on connections in characteristic 0, which have a model. The connection itself has a model on X over W. What was not said this morning is that this theorem is a theorem of Pierre Berthelot. So let me write this. Is that if we look under the, so as was said, and I'm going to assume for simplicity again, because I was already saying saying just before that I'm not going to give to present the whole generality of the theorem. For simplicity, we will consider, I forgot to say, we consider the category unique of X bar over W with logarithmic poles at infinity. So I just write it like this, so that, but those are vector bundles, they are really locally free. So let me write vector bundles here, very small. And in addition, I will assume that the residues are nilpotent. I don't write in the decorations here, it is understood in the category here, nilpotent residue. In reality, the theorem will be true for the same assumption here, vector bundle has to be a vector bundle, but the residues may have eigenvalues which are in Q intersected ZP, but where the denominator is point to P. And that corresponds, of course, to a Temnes assumption. But let me just talk on this. And the theorem of Berthelot here is that if we look, so now we know that this category is the same by Grothendieck as a formal category which comes from the formal scheme. It's the same decoration. And then, as we saw briefly this morning, then Berthelot is telling us that as we take local, because X is smooth over the W's and the Frobenius that needs local lifts, local in the Zariski topology. So locally, we can take the pullback of our connection because it has a model over the W. And then the condition that P is at least 3 is precisely the condition which is going to tell us that the Taylor series which computes the difference between two local lifts converges. This comes from the radius of convergence of the exponential function. So that would not work for P equals 2. That would also not work if W was ramified. If we, instead of taking W, we took a p-adic ring which is ramified. This being said, so we have, let me just write like this. So it's defined over Mick. Let us write again what was written this morning. So it's a safe map here. Is that okay? And I haven't said that. In fact, Berthelot computes that this is true without any poles. Now, if you put log poles, you know, the theorem of Berthelot is that if you forget the poles, if you take two lifts of Frobeni, then the difference of the Frobenius pullback of the connection will define a co-cycle, which is telling you that it is very well defined. So at the end, whatever lift, it's one answer. Now, if you have log poles, you can take a Frobenius which respects the divisor. It's still going to be the case, and this is this one. So that means that is not going to define on the lift you take, which respects the divisor. And and that respects the nilpotent residue. So that is defined here. So now, once I have said, so this is the first thing I had to say. The second thing is that rigid locally means the following, because it's harder to define modular spaces, but the moment we know that the whole category is the same as an algebraic category, then we can define modular spaces. And then we can just look at the theorem moduli. The theorem moduli of vector bundles with when I say connection, is always integrable connection, I apologize, with nilpotent residual. So let me abbreviate this and I fix a rank. So if you like, if I was complete, I could say like this, R is a rank. And I can also fix a determinant, which is finite determinant. So let me write here, determinant, which is finite. So you fix it like chi. Okay, I can also do that. And then by Grothendieck again, we know that the points here, the W points, there's one thing I would not have to say if I was working with stacks, but here I have to say that the W points of this, let me abbreviate this by M. What are the W points here? A priori, because this moduli is not fine, this would be easier if we had a stack. We just know that it represents, there's an object which is really a connection a priori on a cover of W. But because the residue field is finite, it is C1. So then it is a case that the W point is a connection. So W points here. This is a little blah blah, which you do not have if you work more generally with stacks, are objects, ISO classes of objects in MIQ, with all the decoration I said before. So then rigid is just an isolated point. So then I look at M over K. Okay, and I take one, which is defined over W. So M over K means M is defined over W here as a scheme. So M over K means this. Okay, and I look at points here. I look at those points which are isolated, or if you like, zero-dimensional components. And because I have fixed my situation, I will only look at those which come from W points. A priori, I might have an isolated point which doesn't have a model over W, but I look only at those here. So I may assume for simplicity that those isolated points are defined over W. So, and now I can even say injective here, because once I have, those are irreducible local system, then it is a case that there is only one extension which will be, by stability, there will be one extension, which is a W lattice of the connection. So this is one way to say. Another way to say is that there is no formal deformation of the connection.
So when you speak of rigidity, it's keeping the determinant fixed.
I'm sorry, when I
speak of rigidity, you keep the determinant.
I think I keep the determinant fixed because otherwise it's a restriction. I would have to assume there is no B1 on the scheme or something. Of the, so you fix the determinant fixed, this kills that. So if you like, the Zariski tangent space here at such a point is a priori the trace-free endomorphism of the theorem object. So let's see over K. So that's the Zariski tangent space. Is that okay? But here we don't assume it is zero. It might be higher dimensional. It will mean that it's a point with multiplicity. So I'm a little bit slow here because there's no way to speed up, and just to say where we are. So this is, that's basically what I want to say here. Yeah, so that means, so rigid means an isolated point here, which extends, I will consider only those. And of course, if I come from complex geometry, nonetheless, then because in complex geometry, I have only finitely many of those, then for almost all W, this will be fulfilled that all the isolated points here will be here. Is that okay? Okay. So once I've said that, now I say the theorem, so maybe let me write it like this. And forgive, I take my sheet because I don't want to collapse here. So now I summarize the theorem here in this situation. The theorem is that, so the assumptions are like this. So assume we have reached it. So assumption as before. Then one has one conclusion, is that the connection here over capital K with log poles. So let me write bar because we are on the compactification here. Here, and then I can look, as we argued a few times, we can look at the formal completion or not. That's the same information. But for what I want to say, we have to look at the formal completion because that's the definition. And then this is an F isocrystal. So what does that mean? Let me write immediately. So that's the first part of the theorem. Let me write here the explanation. So isocrystal, there is an analytic way to define it. And clearly, I'm not the person to do that. But algebraic is a nice thing about the theory, that it can be understood purely algebraically with two facts. The first one is two properties. I apologize, not facts. The first one is that the characteristic zero connection here has a W model. But this is our assumption. So let me write here W model. And once it has a W model, you can look at the mod P connection. And then you look at this W model. There's a mod P specialization, restriction, I apologize. And then this one should have nilpotent P curvature. And for the people who don't like, so it's a characteristic P connection, which is integrable. And nilpotent P curvature, an easy way to, of course, it has a definition, which is algebraic, not complicated, but an easy way to think is just to say that you can filter your connection as a connection with the property that the associated gradient is spanned by flat section. So that is maybe a better way to say. And then F here, F means, so let's say F means what? Means precisely an obvious definition once you know that you have the Frobenius on your model, and in particular, so the Frobenius pullback of your model is defined. So then F means there is an N, let's say, which is at least one, such that the Frobenius pullback to the power N of, so then I have to take here, in principle, I have to take the formal construction here. And this one is equal to itself in characteristic zero. So it's stabilized by Frobenius. So that's the first thing which should happen if it comes from geometry. So that's the first thing, and now we can write the second property, which is finer, but which happens to rely precisely on the same proof. There is one proof for the two statements, even though the second statement seems to be more involved. So let me write it. So we make one more assumption, in fact, a little bit more than one more assumption. the first assumption is we assume that P is large enough. And this assumption is the one of Vadim, so I'm glad Vadim is here, because it relies on his we need this condition here. The second condition is that.
Sorry, just a quick question. So,
sure.
so you have this. The third assumption is for being split, but you don't assume that for being split to itself as a map, which induces.
No, I don't take this terminology. The proof gives a stronger version, and not stronger, but more closer to reality, because that's how it comes also in geometry, by the way. Not stronger, I apologize. So we assume here, so we make, I forgot to say, I should have said extra assumption. So I want to decorate this F as a crystal structure here. So I take the assumption before plus extra assumptions. The first one is the one coming from Vadim, Enogos, Arsorogos. And the second one is, pardon me?
R is the rank.
R is the rank, yeah, I apologize. It was here, but I didn't know what, I'm sorry. So that's the rank in which you consider the modular. And the second assumption is that every point here in this moduli, which is isolated, so if I take any rigid, so on the moduli here, so one car. So this any rigid here has so it has an nilpotent residue at infinity and meets a Griffith filtration. Well, I should say Hodge filtration, I apologize. Or let's say a filtration. I apologize. Fill of this. So if I had said Hodge, then it would have been clear that it is decreasing, which satisfies Griffith's transversality. And which is locally split. So locally split is equivalent to saying that if you look at the associated graded, it is a vector bundle. And then it's a vector bundle which is endowed with a Higgs field. So you look at, because of Griffith's transversality, so Gre with respect to the filtration of E bar and blah bar, together with Gre of the convection here, it's a Higgs. And I look at the characteristic P fiber of it. And then I can say, whether, so it's a vector bundle on the projective variety. I can ask whether or not it is stable. So I assume it is stable. So before writing the conclusion, let me comment here. The first assumption I commented already with the theory of August Vologodsky. The second condition here, let me motivate it by complex geometry again. If we had a rigid connection on a complex variety, then it would be the case that as we look at the corresponding Higgs point on the Higgs moduli, this point would be isolated as well, because the moduli are isomorphic as real analytic varieties. So one isolated point corresponds to an isolated point. But by Simpson theory, we know that there is a G flow, GM flow on the Higgs moduli, which assigns to a Higgs bundle, let's say V comma theta, it assigns V comma the scalar times theta. And then the fixed point, so then if you have an isolated point, it is stabilized by the Higgs flow. And the fixed point of this Higgs flow are precisely polarizable complex variation of rod structures viewed on the Durham side. So it is natural to, so it's natural to look, so in particular it is endowed with a filtration. So if you take a rigid point in complex geometry, then it will be endowed by a filtration. And then because Simpson is a correspondence on the moduli, if the rigid connection, which is irreducible, is then stable, so then the Higgs point is stable. So here you assume that.
To define stable, you use an upper line.
And I lose, yeah, thank you very much for asking. This is called compactification. I said quasi-projective, but I didn't say that I take a projective compactification. And then the stability condition is the one of Mumford.
So looking at all curves and that's coherent.
Yeah, so it's a coherent, no, it's stable as a pair. Yeah. Is that okay? So in fact, it's something which is fascinating. I'm taking off my time here. I don't need no forgetter. It's something which is fascinating because the correspondence of Simpson, it is never really underlined by people. It looks like, so you have a correspondence, but it recovers all the strong positivity properties of the whole Griffith school. Because the fact that the Higgs bundle to a complex variation of Earth structure is stable, I mean, it is irreducible, it is telling you, for example, that the last piece on the right as a sub is positive, and then the last quotient on the left is negative, and then in the middle it is dancing on X. So it recovers everything. So this is also one aspect of Simpson's correspondence, which is profound and which is rarely underlined in the literature. So here you put it as a condition, a stability, and that's all. And so I assume the extra assumptions, so any here, I should say. I have only finitely many of those, and I assume that this condition is fulfilled for all of them. So I hope the assumption is clear, and now I can write the conclusion. Now the conclusion is that this filtration here, which we put on or if you like, for my completion here, endows the connection with the structure of a Fontaine-Lafayette module. And we know by findings that the structure of a Fontaine-Lafayette module corresponds in a fully faithful way to a crystalline local system on the characteristic P fiber of our scheme over the unramified field. Now, if you were coming from complex geometry, you would still have and because it's fully faithful, you have as many crystalline local system here as isolated points on your moduli. If you were coming from complex geometry, then you would have to go to know something about the Betti structure in complex geometry. You would have to know whether those crystalline local systems, as you go from X over K to X over capital K to X over capital K bar, they don't collapse, for example, to trivial one. It would be faithful. That is an extra argument which does not come out from our method here, which is which we wrote on Shimura varieties, but here we don't. So that's a theorem here. So I think I explained enough the statement here, and now let me let me say a few things. So now I'm going to define first another category, which is very close to the first one, and also close to the work of Vadim, but over W. And this is taken from an idea of Shu. I saw Shu, maybe he's not here, but at any rate, a beautiful work. So it's an extension with log poles of his PhD thesis. So we have this category here. And this, in fact, in the spirit of the lambda line, a lambda connection due to p-adic, which interpolates between the RAM structure in characteristic 0, I mean over C, I should say, with Higgs structure, then you can think that your lambda can be replaced by P as an interpolation. But if you do that, you do the same thing. So you want to interpolate between your connection over W and this lambda line where the lambda line is P. So as you go to lambda equals 0, that means P equals 0, you should get a Higgs object. So this does precisely this. And in fact, it's you find an equivalence here. Let me write here P connection. Which assigns to E nabla. And so here, it's not, so P connection, when you look at the, so here it will be, yeah, so Higgs field here will be really 0. So this is exactly what I said before. So what is a P connection here? In general, it's just a W linear map, which respects not exactly the Leibniz rule, but the P-Leibniz rule. That means you multiply the df, where f is a scalar, by P. So a P connection, let's say P here, of f and s is a local section. This is PDF S plus F. So this is clearly an equivalence of category here. And as you can say, why do you go there? Because it's an equivalence of category, but it shows up in a natural way in the following construction. So before I say the following construction, so let me lift here the inverse Cartier operator, which has been defined by Cartier and on functions, and then generalized by Vadim and August for connections in characteristic P, which are nilpotent. So it comes back to Cartier, but and also the linearity. So here you lift it to this category here. And but now viewed, you have to start with 6 here. So viewed here, it's just an artifact. So it will go from P me to just to me. But 0 here, let me explain here, mix 0, that's precisely those connections with P curvature 0. So again, those connections, mod P reduction of which is complete is spanned by flat sections. And this is just defined by, when we are here, we can go here. As I said, here is just for decoration. I'm here, I can think of it as being a connection. So let me write here. So if we have an object which is here, let me write V prime like in the article with what is the word we used here, nabla prime. So this nabla prime by this equivalence of category can be written as P nabla double prime. And then you assign to it the Frobenius pullback because we explained that it is defined of this connection. So I should put bar here. Okay. So of course, to write this, I don't need this. But to explain where it comes from, it's better because here you see immediately that, yeah, no, we don't see immediately. But I mean, we can feel. Okay. And then let me write the theorem of Schuh here. is that C inverse here is really an equivalence of category. And which lifts the C minus 1 of Vologodsky. Means that's how you start. And it is fully faithful, not equivalence of category, I'm sorry. That if it was proper, this would be an equivalence of category. And if it's not proper, so we have a D at infinity, we can say it's fully faithful. So that is not really computed in his article, but it's possible to complete the argument here. It's fully faithful, and the essential image are precisely those P connection. Zero here. Let me not say. So the zero is in fact ridiculous here because it's a P connection, so the mod P reduction has 0x field, but the residues now, as residues, are P divisible. There's a new condition which shows up because we have a divisor at infinity. So the residues here are P divisible. Okay, so this is one piece of information. And now, why does one introduce artificially? Because all what I said so far, I don't need this P category. So the reason why it shows up is, in fact, again, a construction initially used in this context by Simpson. This is the so-called Artin-Ries construction. So the Artin-Ries construction is going to take, because the moment you don't have any filtration, this P category is completely out of the blue. But when we have a filtration, so let us introduce just for fun the filtered category. So not only we have connections with nilpotent residues, blah, 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 but it's endowed with etc. So we can look at the Artin-Ries construction, which takes this filter, not filter, but category where for which the objects are filtered. It takes it to the category P-mic here. And how does it do when we have a filtration here? I mean, it's a classical construction. Let me put E here. Then inside of the vector bundle in characteristic 0, you can look at the lattice, which is coming from this filtration, modified by powers of P, depending on the level of the filtration you are. And this I cannot explain, but that is also an idea coming from geometry, which has been strongly used by Simpson over C, and in fact, perhaps also over this line, Fargue-Fontaine line, and what Peter wants to do over R, I don't know, but at any rate, he's looking at twisters, so we are here. So let me write this lattice here inside of this. And this lattice is the old one modified by this filtration, and it is modified, let me write it. So when you look at field I, you twist by P minus I, and then I, and then you take, okay. So because the first one was locally split, this one is a new lattice, and the connection, because of Griffith's transversality, induces on this lattice a P connection. So that's a factor.
What is Griffith's transversality?
Pardon me?
What do you mean by filtration?
The filtration on E.
For which you have Griffith's transversality.
For which you have Griffith's transversality, which is telling you that this is a P connection. What's the question? So now, so you have this Artin-Ries construction, so you can apply the Frobenius inverse of this Artin-Ries construction. Makes sense, right? So let us do that. And let us define and this construction locally. Let me underline, this construction locally is due to Shihou. When we have a physical Frobenius lift here, we can define locally, we can define phi here. And then I'm going to tell you how phi is called in our days. You can take, so when you have a lattice like this, which comes from the Artin-Ries construction, then you can take the Frobenius pullback. We said it exists, of 1 over P of this MIC. You remember this P MIC category is the same as the MIC category, so we can take the Frobenius pullback. So this local definition is very beautiful, and because in characteristic 0 we are just changing the lattice here. So as you restrict this to characteristic 0, this is just your Frobenius pullback. So by the very definition, locally, because the Frobenius is a physical Frobenius here, by the very definition, if you restrict phi in characteristic 0, then you obtain the Frobenius pullback in characteristic 0. Okay, so now the following proposition, which is not formulated like this, but which is essentially due to faultings. The following proposition tells you that you have, so we know what we are after. I should say, I will give the terminology later. We want to globalize this flow here. It's going to be called a flow in the spirit of the GM flow. The proposition of faultings is telling you that there is a way to glue this construction to a global flow. Of course, now you can reproach to me, and you would be right, that I will not give you the transition functions because it's very technical. And a big part of the salt is hidden in those transition functions. So it's not completely intellectually honest, but let me just say that faultings gives gluing condition. And those gluing conditions are going to give us a functor from the filtered category here to the Frobenius pullback, so that means two connections. So let me write that. So we have the filter category. So I think, let me write like this for, I apologize, to the mid category. Okay. And those conditions of faultings, when you look at them carefully, they don't violate the nilpotency at infinity. And in the more general version, as I was saying, on a stack with quasi, with residues which are in Q intersected ZP and which are TEM, they are not going to violate that. So respect the nilpotency at infinity. And because you have those explicit construction of faultings, the corollary of the construction, which I didn't write, so it's not completely honest, as I said, but it is honest. It is a case that now you can say, what did I do here? I can look at least at what I did in characteristic P. So I can write phi over FQ, I mean tensor FQ. And phi tensor FQ, what does that do? It does precisely, I mean, we know, yeah, it does precisely the Cartier inverse of the associated graded Higgs object, which is assigned to the filtration. So, so that's August Vologodsky. In particular, because our assumption was that it was semi-stable, then this Cartier inverse is also semi-stable. Because the Cartier inverse respects, it was stable, the Cartier inverse respects stability. So now I come to a close here. I can define what it means that a, so this functor here is defined, is called the flow. And in fact, more precisely, it's called the Higgs theorem flow. And now I can define, so maybe I'll write it here. And Ananth was saying I should not write here. So definition. I can define what it means for an object of MIC with a little decoration we had to be periodic. So let's say periodic of period F with respect to phi. It means like this. It means that, well, I mean, if I take my assumption I had before, I would say I take the filtration I had put like this, and I look at phi of this object. If I forget my assumption, I say there is a filtration which does it. So let me just write filtration. So I can look at phi. Let me write this as E bar, blah, 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 and then 1. Because I'm going to say what is periodic. So I'm going to say it's periodic. I define 1, 2, 3, etc. And F is equal to 1. So I call it 1. And now I define 2. And the 2 I define, you know it, because I have my filtrations here. I take phi of the field on E nabla with all the decoration here. 1. And that defines 2. Okay. And then I can say, so now because I haven't told you what is the main theorem, so I cannot argue in general. So I say, okay, I say it's periodic of period F if there is a filtration on this one. So then there is, let's say, field 2.
So the first one, you just choose any filtration on it?
No, I say it's fit. So I haven't said what is the main theorem. So let me give a general definition. I have a connection here. I say it is periodic of period F if I find a first filtration on this object. Okay. Is that okay? Now that defines via the flow here a second filtration. Then I find a second filtration on this object that define a number 3. And then at the end, number F is equal to number 1. Equal means isomorphic. I think it's quite clear. Okay. And now, okay, so that's the definition. And we have here in the background the work of Lang Sheng-Tzu and the work of Xu imply that this structure here, this F periodicity, so F periodic phi connection here, is the same as a Fontaine-Lafay module. That I'm not going to tell you. But it's not, it is very close to what Faltings says himself. Now I should say Fontaine-Lafay module, Faltings define it for f equals 1. So that would correspond to a unitary, that would correspond to a p-adic local system over x over capital K with values in GLR of ZP. And now this period f here is going to tell you this corresponds to a p-adic local system on x over capital K with values in GLR of Z p to the power f. It's always an unramified period field, period ring. So I don't say that here, but now I can come to the main theorem and then stop here. Well, I have another two pages here. Yeah, so I can come to the main theorem here. Is that no, I have to define one more thing, which Kestutis could define better than me. That's a strong topology on M. M was our theorem moduli. I just write the decoration here, and I can look at the W point, and I look also at the capital K point. In fact, I'm going to look only, yeah, okay. And this strong topology here is defined here by two conditions. It should be compatible with Zariski topology in the sense that, this is just a scheme here, forget where it comes from. So you say that when you have any Zariski open inside of M, then in this strong topology, the point of the W point of this Zariski open should be open. That's the first condition. So you do, because the affines form a basis of topology, you just have to know what it does on U now closed in the affine space. And then it is precisely the induced topology by W. So this is the induced topology. Okay, so I haven't, it's very classical, right? I mean, it's very classical here, you need case to this to go to stacks, etc. So now the main statement here, so the main theorem is that we have this Frobenius, which has been defined by Berthelot, and in fact, which had rediscovered with Johan de Jong last year, realizing that it gives another proof of the, in the projective case of the just first part of the theorem here, using formality theorem of Goldman Mason, which describes the Zariski tangent space to the theorem moduli when it's projective in terms of cohomology and curve product of cohomology. So using Berthelot and this, that was given us another proof of the first part here, which was not, yeah, which was, okay. So, so the theorem here is telling us that, so now we said the Frobenius is defined, and rather than looking at this Frobenius, yeah, I would say the F, rather than looking at the Frobenius on the category, as we did before, we look at it on the moduli, and then only the moduli, only, I can look at the Frobenius pullback on the moduli as a scheme. We don't know that, but because we define it only on W points. So we look at it as just a map from the W point to itself. If you like, write those capital K points which come from W point. Okay. And now the statement here is that this map, just as a map, this one is a topological space. It is continuous, which is maybe not so surprising. but it has one more property, which would be the same as, so to speak, an étal map or proper map. It is open. So most particularly, if you start with an isolated point here, that's going to be an isolated point here. So it's going to respect the isolated point, and that proves already one, just like this, without nothing. But of course, so that gives the first part of the theorem. For the second part of the theorem, you apply the same idea, but a little bit. So now you know that the Frobenius pullback, in particular, you know Frobenius pullback of rigid is rigid, and that's it, because we have only finitely many rigid. So a power is going to be the identity, and therefore it gives you all at once the structure of an isocrystal. P curvature is nilpotent and endowed with a Frobenius structure. End of story. There's nothing more. Now, the second thing is more here. I haven't looked at the Higgs theorem flow. The second thing is that you do the same argument with the Higgs theorem flow. Because you have, under the assumption we said, the points here, all the points you construct with, I forgot to say here, it was correct, but I didn't emphasize. I had said in particular, because the assumption was that the object itself, that was stable, okay? So what you obtain is a point in your moduli, but over W. I mean, stability is recognized on the characteristic P fiber. So I forgot to underline this. So in particular, the flow is going to act. I made it act on the category, I mean, objects of the category, but it acts here on the W points. So again, so it respects, so by the first part, it will respect because it's continuous open, it will respect those points, but with their filtration, you have to make a loop. So it gives two, and that's it. But I wanted to say thank you very much for that.